Hello everyone. My name is Mindu from University of Utah, and the paper I'm going to present today is called DeepLog, Anomaly Detection and Diagnosis from System Logs through Deep Learning. This is a joint work with my advisor Feifei over there, and also Gwendo and Vivi. First of all, I'll introduce some background. Do you know what is this? So, okay, all you need to know is that this is a system event log. Software developers often record critical system events and system status into a log file for purposes like debugging and diagnosis. So, this kind of data is actually available practically on every computer system. And this is a very valuable data resource to understand system behavior. But as you may have noticed, it is very painful to read each log message to know what's going on in the system. So we wonder, can do automatic analysis from system logs? And the answer is, of course, yes. So particularly in this paper, we address the problem of automatic system log anomaly detection. In particular, we want to alert the user if there's something unusual going on in the system. And we also provide methods for user to diagnose the detected anomalies. Actually, this is an example of automatically detected anomaly, and this is a write exception happening in Hadoop file system log. But as you notice, the logging level here is info instead of error or warning, so we can't really rely on the logging level to detect anomalies. And system log analysis is not new. The typical way is usually to first parse the unstructured system event log into structured data. And here, the structured data usually refers to the constant string inside each log message, inside each source code statement that print out that log message. For example, for the log message started service A on port 80, the target log key we want to extract is started service on port, which is just the constant string inside that source code statement that prints out that log message. And we could use a distinct ID to represent each log key. So why this is useful? Imagine that you have a log file with all the log messages ordered by timestamps. And if you could map each log message into a log key, which is the source code that print out that log message. So now you have a source code execution sequence, and then you could analyze this sequence to know if it's going on the right direction. And so the second part is to do log analysis on this structured data, and there are actually previous work doing this. And the first type of method is to use the message count vector, which is to divide the whole time period into different time windows, and then count the log keys inside each window to know if there's an anomaly. And this type of method is only useful for offline batch processing. And there's actually other type of methods to build workflow models from the execution from the log key sequence. But this type of method is only useful for very simple execution anomalies. They are not actually useful for very subtle anomalies. And the common problem of all previous approach is that only log keys are considered, and the parameter values inside each log message are ignored. For example, what type of service and on which part. So the first step of our DeepLog work is also to extract a log key from each log message. And note that here we also preserve the parameter value vector inside each log message. And the first value of each parameter value vector is the time difference of current log message with previous log message. This is the way we include performance anomalies inside our framework. So for this first step of log parsing, we actually leverage our previously published method called spell. This is a streaming log parser. The input is log message, and the output is log key and parameters. It does this using a streaming fashion in using a longest common subsequence-based approach. And you could find the details in our previous publication. And now imagine that we have extracted the log key and the parameter value vector of each log message. So the next step is to use the log key sequence to build a log key anomaly detection model and also a workflow model. And then we could also use the parameter value vector sequence to build a parameter value anomaly detection model for each log key. And the two anomaly detection models are used for anomaly detection, and the workflow model is used for diagnosis. And the two models compose our DeepLog framework. So now I'll briefly introduce the architecture here. In the middle, there are three models we need to build in the training stage, and also we need to use in the detection stage. Now here's the training stage. I'll zoom in a little bit. So in the training stage, we only require normal execution log for training, which means we do not need any information of any type of anomalies to detect them. And this is actually not a high requirement. For example, before every software is put into production, it is usually tested offline to know that it's functioning correctly. And this offline testing log is already enough for our training purpose. So having this normal execution log file, we parse each log entry into a log key and a parameter value vector using our previous spell method, and then we could use this log key sequence to build the log key anomaly detection model and also to construct the workflow model. And then also using the parameter value vector sequence, we build a parameter value anomaly detection model for each log key. And now here's the detection stage. When each new log entry is generated, we first use the log parser to pass it into a log key and a parameter value vector. And then this log key is checked against our previous log key anomaly detection model to see if there's any anomaly. And if it is not an anomaly, we will further check this parameter value vector against our parameter value anomaly detection model for that log key to see if there's any anomaly happens. If either the log key or the parameter value vector is anomaly, we will report this information to the user, and the user could diagnose this anomaly using the workflow model we provided. And if user identifies this as a false positive, we could update the corresponding anomaly detection model using this new pattern. So this is just a brief view of the architecture. So here I'll introduce each model also briefly. So here's the log key anomaly detection model. Note that the log key sequence listed here is actually a rigorous set of logic and control flows generated by the source code. And so this could be viewed as a type of natural language, but only in a more structured way. So inspired by the idea of natural language modeling, we want to train a multi-class classifier over this normal execution log sequence. So think of something as text generation. Given a history sequence, we want to predict the next key to appear. And so then we check this against the actual next log key. If the actual execution follows our prediction, it is normal execution. Otherwise, a log key is detected to be abnormal if it does not follow our prediction. So here we utilize the long short-term memory architecture, LSTM, which is also a very popular utilized architecture for language model in recent years. And here in our architecture, the input of this anomaly detection model is a history window of each recent log keys, and the output is the probability distribution of next key to appear. So for example, in the training stage, this is a normal log key sequence, and we assume the history window size is 3. So the first input is just the first 3 log keys, and our target output is 57, which is we want to train this model so that it could predict 57 as 100% to appear. So here we just tune the parameters to minimize the output of this model with the target output of 57 for 100%. So this goes on and on. And in the detection stage, so now we have a trained model, and we input the actual history sequence as the input of this model, and then for the output, it is actually a probability distribution of all possible log keys to appear. So for example, if you have 100 source code statements, your source code that prints out log messages, then the all possible log keys to appear are just 100. So here is the probability distribution of those 100 log keys, and then we sort the probability we sort the log keys based on their predicted probabilities. And so then in detection stage, if the actual next log key is within our top G probable predictions, we think it is a normal execution. Here, G here is actually a parameter, and later we will see its performance. So LSTM is a type of recurrent neural network. It has a for loop that forwards the output to its input. And if we unroll this network, it looks something like this. And in the bottom, it shows our input. Note that there's a log key as input at each different time step. And also there's a loop that forwards the state of previous time step into the next time step. That's how the history information is preserved. And this is one layer. If we stack this up, we have multiple layers that could remember more information. And so we could get much more history to remember. So now here's the workflow model. So again, the input is a normal execution log key sequence. And we want to update one workflow model for each task. So here there are two jobs we need to finish. The first one is to automatically separate different tasks from this log key sequence. And then the second job is to build a workflow model for each task. There are also previous work that build workflow models from log key sequence, but those work all assume that there's only one task inside each log key sequence, which is often not true. Here we actually designed two methods. The first one is to use our previously trained log key anomaly detection model. We found out that the LSTM prediction probabilities are very useful to hint where this direction should go in the execution path. So for example, this is an example of concurrency detection. And the first three log keys are 25, 18, and 54. We input this history window into our trained model, and we find out that the output is 57 for 100%. So we know that there is a direct path from 54 to 57. And then this history window moves forward. If we include 57 into this history window, the output is 18 for 80% and 56 for 20%. So we know that there is a divergence from 57 to either 18 or 56. But how do we know that 18 and 56 are concurrent? We find out that if we include 18 into the history window, the output is 56 for 100%. And if we include 56 into the history window, the output is 18 for 100%. So this is how we find out that 18 and 56 are always appear one after another, and the order is actually not always the same. So they are probably concurrent. And there are actually other heuristics for other patterns, and you could find all the details in the paper. And also, the second method is that to use the density-based clustering approach. We designed this method because if your purpose is purely want to build a workflow model from the normal log key sequence, you might not want to train an LSTM model to begin with. So we built this co-occurrence matrix of every two log keys appearing together within distance d. The idea is that, like, if two log keys always appear together, then there must be a direction from one log key to another. So we put this log key together, and then we grow from either the left key or the right key based on the co-occurrence probability of this key to other log keys. And you could find the details in the paper. And now this is the parameter value anomaly detection model. We actually built one different model for each log key. The idea is that the parameter values for one single log key have the same dimension, and also each dimension has the same meaning. For example, this is the log messages of a particular log key. Took how many seconds to deallocate network. And the parameter value vectors over time is like this. Note the first value is also the time difference of current log message with previous log message. And this is actually a multivariate time series data anomaly detection problem. and we could use methods like PCA. But PCA mostly focuses on modeling the correlation across dimensions. But here, we are more interested in the value change on a single dimension. For example, if some value suddenly becomes too big. And here, we still leverage LSTM-based approach. But instead of using a log key as the input at each time step, as previously log key anomaly detection model, here we actually use the parameter value vector directly as the input at each time step. And then in detection stage, we check the mean square error between the predicted parameter value vector and the actual parameter value vector. If this mean square error is too big, there might be an anomaly. I'll show a little about this prediction stage. Here is the history window of 5 data points, and we give some prediction here, and then the actual value is here, and we calculate the mean square error between these two values if it's greater than some threshold. Note here, the threshold is actually automatically computed based on the training statistics, and you could find the details in the paper. So this window moves forward, and again, we check the actual value vector against our predicted value vector if this mean square error is greater than some threshold. And then this process goes on as new data are being generated. So how to handle false positives? Note that it is very important to reduce false positive rates in an anomaly detection system, because if you just report too many false positives, then user will simply ignore your warnings. So they might miss the actual very important anomalies. Previously, we have a trained model, and then we input a history sequence into this trained model and get some prediction. And then we check the actual value appeared against our prediction to see if this actual current value is an anomaly. If it is an anomaly, we will report this information to the user, and user could actually diagnose this anomaly using our provided workflow model to check if it is false positive. If it is a false positive, user could report to us, and we could update this model using this new pattern, which is we want to give this history as an input to this model, and we want to update the parameters of this model such that we could output this current value as output. And we actually achieve this using incremental update, so we don't need to train this model from scratch. And now we could remember this new pattern, so next time we won't make the same mistake. Now here comes to the evaluation. So there's this key anomaly detection evaluation, and for this purpose, we use the Hadoop file system log data. This is data generated by previous PCA method paper published in SOSP 2009. And there are actually over 1 million log entries with labeled anomalies in this dataset. So on the left figure, we show that our method achieves the best overall F-merit score compared with previous PCA method and environment mining method, and also our baseline n-gram language model approach. And on the right figure, it is the cumulative probability of top G predictions, means by how many percent the actual next log key is within our top G predictions. For example, with about 89%, the actual next log key is exactly our top first prediction, and with about 100% accuracy, the actual next log key is within our top 5 predictions, which shows the validity of our approach to use LSTM model for this type of prediction. And here, this is the parameter value anomaly detection model. For this evaluation, we generate our own OpenStack cloud log because previous Hadoop file system log has too few parameters to learn. And this log data is generated on Cloud Lab. We constantly run VM creation and deletion operations, and we also inject performance anomalies to see if they could be detected. Here, the vertical bar, the y-axis here is the mean square error between predicted value and the actual value. And the right horizontal bars are the thresholds automatically computed based on different confidence intervals. And the 4 figures are just detection results of 4 different log keys. Here we could show that we could successfully detect the anomalies in different timestamps. And we also identify a possible false positive at here based on which confidence interval you choose. Now here's the LSTM model online update evaluation. Here we utilize the HPC log with labeled anomalies. This log data is also available online. We use this log because it has the pattern that most log keys only appear in the latter half of your system log. So if you only use the first several percent of log data for training, there might be a large percent of log keys may not even appear yet. So we can see that from the left figure to the right figure, even when we increase the data set for training, the F measure is not improved by much. But with our online update approach, we could increase the F measure by a very large percent. And so, which means we reduce the false positive rate by a large percent. Here's the case study of network security log. And this kind of log data is actually much easier to detect than our previous use log message. And for this purpose, we use an also online available data set. This is a HV visualization conference challenge. And the purpose of this challenge is to manually find the network anomalies using visualization techniques based on the logs they provided, for example, firewall log and intrusion detection system log. And we show that we could automatically detect almost all anomalies except the last one, which is an undocumented IP address anomaly, because we assume that we do not have any prior knowledge. But if we have the prior knowledge of, for example, documented IP address, this is very easy to detect. Here is the workflow construction evaluation. This is a constructed workflow of VM creation task of our previous OpenStack cloud log. And we could show that how does it help to diagnose anomalies. First, we detect an anomaly in the last log key 56. Took how many seconds to build instance. We found that this value is too big. And also we identified another anomaly here at 53, a time difference anomaly, which means that the time between 52 to 53 is too big. So the identified anomaly because instance took too long to build because of the transition from 52 to 53. Note that 52 here is creating image. So which means that the VM creation step takes too long time because of this creating image operation. And our injected anomalies during VM creation, network speed from controller to compute node is throttled. So in OpenStack VM creation task, the controller needs to copy an image from controller to the corresponding computing node to create the image. So this, because of the network speed is throttled, this VM creation becomes too slow. So here we show that our workflow, our constructed workflow could help the user to pinpoint where this anomaly happens. Now, to summarize, LSTM is a real system log anomaly detection framework. We use DeepLog is a real system log anomaly detection framework, and we use LSTM to model the system execution path and also parameter values. We build workflow models to help user to diagnose the detected anomalies, and our framework also supports online model updates. So this QR code is for our actual paper, and you could thank you all for your attention. And now I'm ready to take any questions.
Very nice talk. Really enjoyed it. Can you comment on why do you think LSTM works better?
Yeah.
And another question is, you mentioned one of the parameter is this 3 tuple that you use, and so you're using this 3 key sequence, and if you increase it, so this length of key sequence, how would that impact the results?
Okay. Those are very two good questions. And the first one is why LSTM performs better. And the reason is very simple, because LSTM is very good at modeling the history sequence. And I would assume compared with previous methods, LSTM works better. Previous methods, the offline methods count the number of log keys within each time window. So this does not preserve the order information of the log keys. And also another method is to use the workflow model. But the workflow model could only reveal very simple patterns of the log key sequence. But LSTM, with millions of parameters, it could remember the history information very well, so that it performs better. That's why now the language models also use LSTM to model the very much more complicated human language. So this is actually an easier task for LSTM. And the second question is, if we increase the history window, does it affect our performance? For LSTM, it works very well, because even if you increase the history window, LSTM could learn that only the most recent log keys are relevant to our prediction. But it does not. If you increase the history window, it will affect the traditional language model by a very large percent, because traditional language could, well, I won't introduce the details of traditional language model, but its performance will reduce a lot if you increase the history window. That's why we use LSTM. Yeah. Thank you for the question.
Thank you for the interesting work. I have a question about in your training stage. So how do you ensure the coverage of the program states that you?
Yeah, that's a very good question. We can't ensure that, actually. We could only guarantee that whatever we see in the training stage, we could make sure we will treat the same thing as normal in the detection stage. But we can't ensure whether this training stage could include all possible possibilities.
Okay, so does it incur any false positive more, or did you see?
Yeah, I guess if the training stage doesn't have sufficient training data, it must have more false positives. Yes.
Okay. I have another question. Is that so? You mentioned that so you train the system logs. So do you mean a specific program, or it's a system wide or whole system logs?
You mean system log?
Yeah.
We actually target any kind of system log produced by any type of software or computer system, and we do not generate our own logs. So.
Okay. So do you consider the dependencies between different programs running on the system? Like
yes,
yeah.
That's a very good point. We actually, I think one of our future directions is to analyze the correlations across different system logs. That's a very good question.
Thank you. Yeah.
Thanks.
That was a great talk. Just a question around unsupervised versus supervised learning. How much percentage in the initial would you send to qualify from supervised, wherein you would have human input? And what was the reduction over a period of time when that supervised input came in? Do you have some statistics around that?
So you mean like?
Yeah.